Hey everybody, welcome back. Um, so I don't know if you guys can hear what's going on in the background, but it is not yet 3 a.m. But my cat has decided that it is time for her to go fast and do all of the things, and so she is currently playing with some of my kids' toys. So if I'm distracted, or if you hear noises, or if something gets thrown in my face, that's what's going on in my house right now. So I will try and work through, and we will just get this show on the road. Okay, we are talking chapter 7. Okay, I'm going to make this video, or this stuff today, one video. I'm going to try and get through as much stuff as I can. The nice thing about videos is that you can pause, rewind, write down things, and I can go kind of fast through the slides. So I'll kind of skip around and get to some stuff that I think is important for us going into our Mastering Chem for Chapter 7. Okay? We're going to start with energy. So Chapter 7 is all about thermochemistry, thermo being heat. And so we need to talk about some things with heat and energy. Okay, here's some definitions that are going to be really important for you to write down. This is kind of the overall general definition of thermochem. Here is the definition of energy. And then work and heat are two important things for us for this chapter. Work, and if you've taken a physics class, you might be familiar with work more so than somebody who has not taken a physics class. But work is going to be a force acting over a distance, and it's a energy. It can be in the form of work, or in our case, energy can be in the form of heat. Those are the two forms of energy that we are particularly concerned with for now. Okay, so work and heat. And from Gen Chem and Honors Chem, hopefully you have a little bit of an idea of what is heat, being the flow of energy caused by a difference in temperature. And so when you feel something as hot, that energy is flowing into your skin or your hand or whatever from whatever you're touching or feeling. Okay. Okay, so we can think of energy as a quantity. Okay, and this quantity can be made of two different things: heat and work. Okay, and these systems can flow, the energy can flow in and out of these systems, or these objects, or these chemicals, or whatever we're dealing with, okay? And so we can go out of an object or a system, and we can go into an object or a system, and heat can go in or out, and work can be done on or done by, and that's how energy flows. As work is being done on the system, or work is being done by the system. Okay, that's how we flow in and out. Okay, we don't need this. The definitions here aren't really important. I'm looking at the image over here on the right hand side of the screen. Okay, so and particularly this right here, where we have that transfer of energy as work. Don't really have a whole lot here due to heat. Maybe a little bit of friction from the pool ball on the pool table, but the majority of this energy transfer is being done as work from one pool ball to the other. Okay, so just to kind of, and there's that force acting over a distance, and that distance would be from one pool ball into the next. Okay, so there's our an example of work if you're not necessarily familiar with it. So kind of a flow chart of types of energy, or at least types of energy that we are concerned with right now. Hopefully you're all familiar with the terms kinetic and potential energy. Kinetic energy is due to motion. potential energy is due to position. In specific, what we're looking at here is thermal energy. And remember, heat or temperature is a measure of the speed or movement of particles. And so thermal energy is a type of kinetic energy. Okay. Over here, this side, chemical energy, those molecules are held together. Oh my goodness. Molecules are, sorry, the cat just went crazy with the little platypus. Molecules are held together by bonds, right? And so those bonds take energy to exist. And so when we create bonds or when we break bonds and we go through chemical reactions, we're dealing with chemical energy. And so that is a type of potential energy. A lot of the second half of this chapter is going to be focused on the chemical energy. We're going to focus on heat and some of the thermal energy stuff in the first part. Okay? I'm going to skip around here. And I want to go to this one. Don't really need to write a whole lot on this one. This is just talking about how we get to the unit of joules. Okay, so kinetic energy. If you take physics or if you have taken physics, this equation is very familiar. And the way that these units would work out, mass being a kilogram, velocity is a meter per second. Oh, that's a 2, not an S. Okay, and then we square it, so we have meter squared and second squared. This is a really loud and busy unit, and so it's been abbreviated and cut down to joule. And so a joule, Joule, is the unit that is used for energy, and it's equivalent to the amount of energy to move 1 kilogram at a speed of 1 meter per second. Okay, so that's what that is equivalent to. We will be using joules mostly, and maybe some kilojoules as our unit, so that would be kJ for our energy units for this chapter. This is a slide that I want you to pay attention to here, particularly this little conversion table. So we have joules. We also have calories, and if you remember back to your Gen Chem or Honors Chem days, you probably, maybe, depends on who you had, did a food burning lab. I know we did that in my class. I know Mr. Burkett does it in his, where you're looking to try and calculate how many calories something has in whatever piece of food, a piece of popcorn or a Cheeto or something like that. And so calorie is another form or another unit for energy. And so we can convert between calories and joules. We can convert between big calories. That's what I call these. Calorie with a capital C is essentially a kilocalorie or 1,000 regular calories. Okay, and we don't usually use kilowatt hours, but if there's a question on your homework that talks about conversions or gives you a unit in kilowatt hours and you need to convert it to something else, you have that. Notice here that 1 little calorie is equal to 4.184 joules. And so if we have if we're looking for kilojoules, that's multiplying by 1,000. That is 4,184 joules equals, I guess, 4.184. You know what I'm trying to say. So to get from joules into kilojoules, you multiply by 1,000. That's what I'm trying to say. That's my message here. Okay. Let's see here. Where else do we need to go? Let's talk a little bit here about first law of thermodynamics. Okay. So the first law of thermo is the law of conservation of energy. And if you remember the law of conservation of matter or mass from like balancing equations, it's the same thing except we're just talking about energy. Okay, so we cannot, I don't even know if it says it on this one. This one right here. You cannot create or destroy energy. You can simply transfer it between the system and the surroundings, from one object to another, from one area to another, from one kind of energy to another kind of energy. Maybe that's light to heat, or motion to sound, or things like that. Okay, so you cannot create or destroy energy. You can only transfer energy. Okay, and so here they use the example of some mechanical potential energy in the form of a spring. You compress the spring, that energy from that compressed spring is then transferred into a ball that gets thrown up into the air. Okay, law of conservation of energy. You cannot create nor destroy energy. Okay. So yeah, let's look at this here just quickly. So delta, just like in math or any other science class, delta means change. Okay, so the change in the energy of the universe is always going to be zero, because we know that we cannot create nor destroy energy, right? And so it's just transferred within that within the system, if the system is the universe, and so delta E is always going to be zero. In order for that to be true, the change in energy of the system has to change in energy of the system plus the change in energy of the surroundings has to equal zero. So the energy that the system gains has to be equal to the energy that the surroundings loses, and vice versa. If the system loses energy, that is gained by the surroundings for a net total change of zero. Okay, and this graphic kind of explains that as well. Okay, kind of running close on time here. Let's see what else we can get to. A quick discussion on, well, where's it at? System versus surroundings is what I want to get to. I don't know. I don't know where it's at. System versus surrounding. Here we go. So essentially, the things that are doing the changing. Okay, so a chemical or a piece of material or something, some molecules that are undergoing change, that is going to be defined as the system. Okay, everything else is the surrounding. So if we have something dissolved in the water is, remember, just that facilitator of the reaction. The water doesn't participate in the reaction, and so the water would not be the system. It would be considered the surroundings. Okay, the beaker, the air, your hand, the universe, whatever, would be considered the surroundings. Small individual things only would be considered the system. Okay, running out of time. I would suggest going to watch those key concept videos. You should be able to answer at least a couple of the Mastering Chem questions, but those key concept videos will at least give you a starting point going into this chapter 7 stuff. We're going to continue to hit it hard once I get back. Okay, see you guys later. Go get on the Mastering Chem. Welcome back. I'm excited to see you on Friday. All right, see you guys.